Okay, let's discuss the continuity equation. So here we have a turbine, and we're not really going to use the fact as a turbine. We're just looking at the continuity equation in this example. But either way, turbine is the scheme for a turbine looks like this. Basically, we have steam entering through here and exiting through here. And you can see the inner diameter goes from 0.6 meters to 4.5 meters. And we also know that at this end, the steam is at 60 bars and 500 degrees Celsius and has a certain velocity of 100 meters per second. And it leaves as a saturated vapor at 0.6 bars. And we're asked to find the mass flow rate, that's 1. And also the outgoing velocity. So we know the velocity going in here. We don't know the velocity coming out. So let me just sketch out exactly what we're seeing here again. And omitting the geometry because it's right there. So we know that we have some sort of steam. We don't know what. I'm going to write ST for steam. And it comes in at 60 bars. Okay. And 500 C. And it has a velocity here of 100 meters per second. Okay, so I have 100 meters per second coming in, and that's going to be velocity 1, and this is going to be T1, and this is going to be P1. Okay, and then it leaves it here, but we know when it does leave it, we know first of all that it's going to be saturated steam. Okay, and we also know that it's going to be at P2 here is 0.6 bars. And we don't know the temperature, but we don't know the velocity, and we don't really know much else. Okay. So the governing equation for mass flow rate is going to be, well, really the continuity equation. I'm just going to go here. So if we're looking at a mass flow rate, as we saw in the notes, it's the integral of the density, which we'll assume for this case remains constant, of the velocity with respect to the area here. So we're going to assume this thing, if you look at it side view, it's a pipe. It's a the cross-sectional area for this thing is circular. So what we also can assume is that through this circular, since we're not really discussing flow profiles here, we'll assume that the velocity is constant along any intersecting cross section. So that means that we could take the velocity out of the integral. And by and large, if for our class, unless otherwise specified, you can just assume that m dot is rho velocity a, like that. That's fine. And I discussed that in the notes at length. But I also discussed the fact that rho, which is the density, is 1 over the specific volume. So we can also express this thing as vel A over V bar. Okay, so that's going to give us the mass flow rate. We don't know the mass flow rate. We do know from the conservation of mass that any mass coming in here is going to be equal to the mass coming out, since there is no accumulation. It's a steady state device. There's no accumulation. Steady state meaning nothing is changing with time, and so there wouldn't be any accumulation steady with time. But either way, there's no discussion of accumulation. There's no reaction or anything like that. So we can assume that the mass on the left end of things, which we call state 1, is going to be equal to the mass coming out on the right side, which we'll call state 2. So that means, of course, that the velocity 1 times area 1 divided by the specific volume 1 is going to be equal to the velocity 2 times area 2 divided by the specific volume 2. Okay, so we know the velocity coming in. We know, well, so I'm gonna mark that here. I'm gonna mark it with red, so it's a little bit different. I'll mark what we know in red. we know this velocity. We have the diameter, so we can get the area. And we know the area here as well. We don't know this. This is what we're looking for. And then we're not really they're not really specifying the specific volume for any of these things. They're giving us for state one, the pressure and the temperature. So just from that alone, we could probably determine the specific volume, because only two intensive variables are required to define a state, as we've discussed. So what we will do is go to the back of the book to the steam tables, and we don't know if this thing is saturated or not. So we will first go look at the saturated steam table, and we know that it's at 60 degrees, 500 degrees Celsius and 60 bars. So if I'm looking at the saturated steam, which is right here in terms of convenient temperatures, I could see that the highest temperature at the bottom here is 374.14, which corresponds to the critical temperature of water, meaning that we cannot have water, liquid water, above this temperature, no matter what the pressure is, no matter what's going on. And just to convince yourself, we can look at the saturated water in terms of pressure. It's the same information again, just this one is organized in terms of convenient pressures. And we know that we have 60 bars, and when we look at 60 bars, the corresponding temperature here is 275.6. So we know for a fact it is not saturated. So our options are that this is going to be a liquid, which really wouldn't work well for this turbine, since we are specified this as steam. So it's more likely going to be superheated steam. So we're going to go to this table here, which discusses superheated water vapor. And we're going to look at pressure of 60 bars. So you can see here, these are pretty low. So I'm going to keep going until I reach 60 bar, which is right here. And I need a temperature of 500 Celsius, which is this first pink thing here. So that means that I know my specific volume right there, and I can make a readout of that. So that's my first specific volume at the entry. So that's V1 bar. And I'm just going to copy it over since we will need it. So we know this thing, now we know it. This is going to be, what the heck was this? 0.05665, okay? And this is meters cubed per kilogram. All right, and this one, the second specific volume, well, we know only one variable at the end. We know that the pressure is 0.6, but we are told that it's saturated. Okay, and we can assume that the quality is 1, since the entire thing is gas here. So we can go to the saturated steam, saturated water table here, and look at pressure of 0.6. So this table here is organized in terms of nice pressures, since all the pressures are nicely incremented. And I'm going to go to 0.6 right here, and I can actually read it. I don't need the temperature for any calculation, but the temperature at that point is 85.94. What I actually need is the specific volume of the gas. Okay, because I'm going to assume the entire thing is gas, steam, and so it's going to be 2.732. Okay, so I'm going to go put that down here, and I know now that this is here 2.732 meters cubed per kilogram. Okay, so now in my continuity equation, again, I'm going to just mark everything I know red. I know this one, I know this one. The only thing we don't know is velocity 2. So you can just substitute everything in. This equation does not require special units. It's any units you want. You can mix and match whatever you want, as long as the specific volumes both have the same units. They do. The velocities both have the same units, and the areas both have the same units. That's the only requirement. But I can have areas in customary system. I can have velocity in SI, and I can have the specific volume in a mix of those two. It doesn't really matter. These specific volumes do not affect the results of the other variables, as long as it's consistent. for that specific variable. So I'm going to substitute everything in. I'm going to do that right here, and I'm going to omit. No, I'm not going to omit. I'm going to put everything in. So I know that I have 100 meters per second. That's velocity 1 coming in. And I know that my area is pi r squared. I know the diameter here is 0.6. So it's pi times 0.3 meters squared. And this entire thing is divided by this thing, 0.05665 meters cubed per kilogram. Okay, that just took care of this left-hand side of the equation. This whole thing is going to be equal to, well, vel2, I don't know it, I want that. Area 2 is pi r squared again. Pi, the radius of that thing, which is 2.25 meters squared. And all of this divided by that specific volume, which is 2.732 meters cubed per kilogram. And just to show you here, well, several things you should really notice here to save yourself some computation. You don't got to plug any of those pi's in because the pi's cancel. See that? Pi by pi. This area is in meters. This area is in meters squared. This velocity will end up being in meters per second because it's going to be whatever that is. And these two specific volumes are meters cubed per kilogram. Okay, so I'm going to punch that all into the calculator. Okay, and I'm going to write here our second velocity as a result, and I'm going to write that in red here. We know here that based on that equation, velocity 2 is 85.7. This marker is not awesome. Give me a second. I'm going to write that in black. So the velocity 2 here is 85.7 meters per second. 85.7 meters per second. And if I were asked for the temperature, which I was not, I can also give that the temperature here from the table was 85.94. But I don't need it. I'm just going to write it for completion's sake. Now everything is kind of the same on both ends. Okay, so that's cool. So now we have the second velocity. To get so we're not done. We were asked for both the final velocity and here the mass flow rate. So we got this thing. We didn't get this thing yet. Okay, so since the mass flow rate, that's going to be fairly straightforward. Since the mass flow rate, as we wrote, is velocity times area divided by specific volume, pick either one of the states. State 1 or state 2 is going to give you the same answer. So if we use state 1, then we know that we have 100 meters per second for the velocity. The area, again, is pi times r squared, and the diameter is 0.6. So the radius is 0.3. So pi r squared, and divide that by the specific volume. Okay, and you will notice now that what cancels is I have meters squared times meters, that's meters cubed. The meters cubed cancel. Then the kilograms is going to be 1 over 1 kilogram. So it's going to be kilograms. And this thing is 1 over second, so it's going to be kilograms per second. And lastly, my m dot is about 500 kilograms per second.